Okay, as many of you probably noticed yesterday, we have our first assignment posted.
It is easy.
There's a bit there. I think I used the term behemoth yesterday.
Yes, you did.
It's a bit of a behemoth. I did cut one problem, so we're down to 21 problems instead of 22 problems. I don't know how much that helps, but
Yeah, maybe more than we expected, I think.
so I wanted to talk a little bit about expectations just because this is the first time a lot of you have had me in a class before, and I try to be as straightforward as I can with the instructions. But that doesn't mean there aren't questions, so I want to make sure there's time to address what the expectations are for an assignment like this. So as you can see from this, I'm not particular about whether your answers are typed or handwritten. I don't care too much about exactly how you structure your answers to this, as long as the graders can read them. In a 46 student class, when we're unsure about how one of the graders is going to be able to interface with the class, the more work that you can do to make the grader's life easier will certainly make turnaround times easier, better. So I know that it takes a little bit of extra effort to make sure that your assignment is, if there are multiple pages, that they're in the appropriate order of the questions that are asked on the assignment, that where your answers are and your work is straightforward and legible, easy to see and read, your process is easy. Whatever you can do to make the grader's life easier will end up being appreciated. So just make sure and double check that images are quality. They aren't incredibly blurry like this homework assignment is. I had to do what I could to go from a low resolution source. I did what I could in the amount of time that I had. I was planning to clean this up eventually so that it's a little bit easier to read and understand. This is the time that I had for the moment. So if we actually open this up, make sure everything you submit, there's a single file. So combine everything into a single PDF. Please don't submit something that is a bunch of files and we don't know what order those files address the questions. They might not all load in the same order that you have numbered them or that you have assumed. Make sure there's a single file combined into a single PDF with all of your answers. I know I missed at least one of these. So if we look at, if you have the book, it's important to note that the exercises are found at the end of each section and the problems are found at the end of each chapter. Even though they are numbered in ways that look fairly similar, the exercises are chapter.section-problem. And then the problems are chapter-problem. So they look fairly similar. Where I could, I tried to make these a little bit larger or easier to read. There are also a couple of symbols that we have not gone over in this table, but I wanted to make sure is a little bit clearer as to what this is. We talked about big O notation, and we talked about big omega notation and big theta notation. But there's a little o and a little omega there. What do those mean? Those of you who've seen complexity before, what is little o and what is little omega? Good thing we're going over this.
Familiar.
Excellent. So the way that I'm going to map these is to mathematical operations, but instead of it representing a value, it's going to represent asymptotic notation. So big O basically is the equivalent of a mathematical less than or equal to. This says that the order that this runs in is less than or equal to the one that is disseminated. There may be some inputs for which this runs at a lower order. If we say big O of n squared, it means that the worst case running time is proportional to n squared. Little o is the equivalent of strictly less than. If you say little o of n squared, that means that we don't know how asymptotically close to n squared we're going to get. We just know there is no input that runs at n squared. It might cap at n log n. It might cap at some asymptotic point that we can't prove, but we just know it is strictly less than n squared. There's no input that runs at n squared. Every input runs less than that, but how much less than that is not specified. So big omega, we said, was greater than or equal to. It gives a tight lower bound, and little omega is strictly greater than. It just says that there is no input that runs at that order, but we could get arbitrarily close asymptotically to that. It gives you a lower bound that is never reached. And then theta is precisely equal to. So again, just ways that I like to see this in terms of something that you've probably seen before. If we're looking at numbers, less than or equal to can be equal to, but we know it's either equal to or it is less than. Something that is strictly less than gives you a bound that says it cannot be this value, but it could be any value that is less than that. Just take the idea of this related to numbers and now apply them to function orders. Are there any questions on that? Yeah.
Sure. Is it possible that there are rows within the theta column that are in?
So you're answering here either yes or no as to whether it says that whether A is one of these orders of B. So there will always be either a yes or a no there if that could be stated. Like in the same way that 17 and 36, if we were to place 17 and 36 as our two numbers, which of these symbols could we apply? Is 17 less than or equal to 36? Yes. Is it less than 36? Yes. Is it greater than or equal to? No. Is it greater than? No. Is it equal to? No. So that's how you fill in that column, or I guess this row of the 17 and the 36 compared to each of these associated orders, except that we're not looking at numerical comparisons. We're looking at orders, asymptotic complexity of those inputs. Then there is an ordering problem. So you're going to take all of these asymptotic functions and you're going to order them from most efficient to least efficient. But do note that I added some bold text here. Since the book talks about the order that is, or the function that is log star, and it's not something that I find particularly necessary to go over in class. If you have the book, you can look at it and think about it and incorporate it into your answer. But since I'm not requiring that people have access to the book at this point, I'm saying ignore everything with log star. I'm not going to go over it. And if you don't have the book, you wouldn't know what that means. So for instance, this is a function that includes log star. So is that. So is that. So just don't incorporate any of these that have log star somewhere in them. This does not say ignore any term with log with an asterisk that I later go explain. So please do include anything that has the log itself. Just ignore those that have log star. I don't need to see where those fall. Wherever there is a book thing, a book problem that says prove something, prove or disprove, I am not looking for a mathematical proof here necessarily. So it does not need to be a formal mathematical proof. I'm just looking for an intuitive argument, something that I can't argue with. What is an intuitive argument? It is something that is complete and it is correct. So you have made an argument that I can't poke a hole in and say you didn't consider this aspect. Even if everything you disseminate is correct, you must answer the question in a way that I can't say you didn't answer this portion or for these inputs, or your intuitive argument should cover every case. then I also shouldn't be able to poke logical holes. Like when you disseminate something, you are wrong about that. So just make sure your intuitive argument covers that, but I do not need, again, a complete math proof. So I guess as an example of this, here we have f of n is in big O of g of n, implies that g of n is in big O of f of n. A mathematical proof would be either a proof by contradiction, I guess a proof by counterexample. You could find an example of this where that isn't the case. You would provide the counterexample and then go through the proof by counterexample. I don't need all of that. If you can find the counterexample, great. Give me an f of n and a g of n for which that is not true. If you're looking to prove it, rather than go through a straight proof, you might intuitively say, for all f of n, if it's in big O of g of n, then this is what this means if we reverse them. It means that this has to follow logically that, etc. Lay that argument out for me intuitively. And I'm not going to look for if it is mathematically perfect or it has the appropriate setup. I'm just looking for, do you understand whether this is true or not and why and how you're thinking about it? So explain that at a level of detail that I can see your thought process. Then, yeah, that's just true anywhere the book says prove. Prove this identity. Again, doesn't need to be a proof, just provide an intuitive argument. And there's a couple things here we haven't done yet. So everything 4.4 and on we have not covered, but we will cover probably today. We're going to be doing the recursion tree method and the master method. So if you looked at this and didn't know what those were, that is coming today. Are there any questions on this document from what the opportunity you've had to look over it? Yeah.
If we're doing it on like paper, do we need to include the question with each one, or if we just write the?
That is a good question. If you include the problem number, that is probably good enough. But I have had TAs in the past say that they really like it when the problem is written, and it makes it a little bit easier for them to, instead of having to refer to another document, what is the question that this is answering, and it's embedded on your sheet, it saves them a little bit of time. So you'd like to pass on some goodwill to the grader, write the problem, but I will not have them deduct points for that not being there. Other questions? All right, I know this is a lot. I want to mention that the expectation here isn't that you go work on this completely independently, come up with all of the answers and turn it in. There will be some people in here who are capable of that, and that is wonderful. But the general expectation is that this is going to be a bit of a back and forth between your understanding, asking questions of me in office hours, having me walk you through parts of this or how to think about some of this. So please do not feel bad, like you're behind in the class. If you have questions about this, if you want to come get some answers, I expect that most of the class will struggle with something at some point that I can help with. So that is what I am here for, even if it's not strictly in my office hours. Let me know how I can be helpful, and I would be happy to work with you to get a better understanding of this, get started on a lot of these kinds of problems. That's what I am here for. I anticipate this is going to be a back and forth. That's how learning happens, is that you are pushed a little bit beyond your comfort level, and then I am here to help you meet that expectation. So I expect to be spending a significant amount of time helping people make progress on this and turn this into the best work that you can provide. I do not expect you to just go off, no contact, do this perfectly without assistance. Question?
Want to reiterate, it's Wednesday night?
Yeah, Wednesday night. It'll be midnight Wednesday night. So you have a week plus however long we have until midnight tonight. But since there are a lot of problems here, and you will get stuck in ways that you don't currently anticipate, please start early. I will have more available, there's more availability spread throughout the week for me than there is on the day it's due. If half or more of the class is waiting until the day it's due, and there is a ton of demand for office hours on the day that it's due, I won't be able to do as well as if that demand is spread out over a wider period of time. You will get more and better assistance if you get started early, get stuck early, get help early. Again, that anticipation, I am planning for there being a lot to that. Of meeting you halfway of understanding this. Any other questions? Any concerns? As I mentioned, this is going to be the only book assignment for a while. The next at least couple assignments are going to be project related. So there will be more coding, more implementation. This won't just feel like a math class, but this is a very math heavy, textbook style heavy topic. So I think that is the best way to assign and get practice on this. Okay, where were we? Middle of recurrences. How much of this did we have left to go? We were in the middle of this example too. We had just finished it. Okay, so the last example that we saw with regards to the substitution method of recurrences is that we were looking at binary search, trying to come up with an asymptotic runtime via recurrence analysis that matched our intuitive and knowledge that binary search is a logarithmic time algorithm. And we found that. One thing I wanted to clarify just a little bit, I think it matches one of the questions that was asked last time, is kind of a how are we going from this and solving for how do we get something that was logarithmic from this? And that is, I know it's not visible because it's the very bottom, the very last line here, this in general t of something plus kc, we wanted to get that to logarithmic. The reason we set this to 1 and solve the n over 2 to the k as 1 is that is our base case. When we reach the base case of this recursion, that means that we've gone through all of the work to locate the item, whether it is in the list or not. So t of 1 is all of the work that we needed to do at t of n over 2, t of n over 4, t of n over 8 to get down to that base case t of 1. So how much cumulative work has been done by the time we reach t of 1? That's going to be solving for k with respect to n. We'll see t of 1 plus the actual amount of work that we went through to get to that point. So that's why we set n over 2 to the k to 1. And as we solve that, then we just multiply both sides by 2 to the k, take the log of both sides, and we see that k is log n. That's how much total work had to be done to get to that base case. Yeah.
I was kind of confused about that. It looks like we kind of lose KC do that, and I'm wondering what happened to it.
Yeah,
It looks like
because
we should be
t of 1, the cost of t of 1 is constant. So as we do this, the question is how many copies of this n over 2 to the k have we done? Because each time we do that, we add 1 kc. So how many kcs are there going to be? There are going to be a logarithmic number of kcs. We're saying that this runs a logarithmic number of times to get down to k sub 1. So we multiply the kc times log n. We're doing kc work each of log n times.
I mean, that sounds like it should be, we should end up with n log n.
Because k in this case is the value of, let's see, I think it's embedded around here. Basically, we have the t of 1 plus c times the number of times, so we set k equal to log n. So when we substitute, because we have c times k, and we know that k is equal to log n, we can replace the k with the log n. And we see that the complexity of a size n problem is the base case plus a constant times k, which we found to be equal to log n. Yeah. I just felt like at the end of lecture, there was something nagging at me, like I didn't answer someone's question well. So I wanted to make sure that I could come back to this and explain it so that the class as a whole could feel like this work makes sense, hopefully. How is everyone else doing with that? Does that process make sense as to how the back substitution is working, how we came up with this complexity, what it means with respect to the problem at hand, tying it back to binary search? Okay. If there are other individual questions on that, I'm happy to answer them or work through it with you during office hours. I should also mention that I have a small meeting, a quick meeting at the start of my office hours today, so I'm delaying them ever so slightly. I don't think it'll take longer than 15 minutes, but here we go. So second method for solving recurrence. We have our substitution method, and that works all the time. The substitution method is not particularly visual. It is a more logical, mathematical way of understanding a recurrence. There is a more visual way to look at recurrences as well. So let's look at the recursion tree method. This is not a mathematical, so if I ask you to prove a recurrence, the recursion tree method does not frequently work as a math proof, but it does work as a way to ground yourself in the problem, visualize the problem, and then you can verify your answer that you get from the recursion tree method with the substitution method in a way that works as a much more induction type proof. So let's give you an example. We're going to be drawing out a recursion tree where the root of the tree is going to be the problem at size n, and its children are going to be the problems that the problem of size n gets broken down into. And each of those children are going to be the problems that gets broken down into. And so we're going to draw out the recursion structure as a tree. So as an example, I will give you the following recurrence. T of n equals 3 t of n over 4 plus theta of n squared. Anyone able to or willing to interpret this for me? What does this recurrence say about the structure of this recursive problem? We don't know what algorithm this represents. We just know that there is some algorithm and it can be referred to with this recurrence relation. But what do these numbers and symbols represent here? What can we state about this problem? Yeah.
That's recursive. We've got 3 subproblems.
Yeah, we have 3 subproblems. And from there,
We add a constant n squared.
yeah, the combining process, when after we've finished breaking the problem down and we've come back from that recursion and we're ready to combine these subproblems into the solution, the process that takes is quadratic with respect to n. What are the size of each of those subproblems? We have 3 subproblems, but how big are they? Yeah, they're 1/4 the size of the original. So this is the equivalent of saying if we have a problem of size n, when we break this down into its 3 components, since there are 3 components, each of those problems is of size n over 4. So one step later in this recursion, after we've recursed and we're calling this on its subproblems, there are 3 problems of size n over 4 to solve. When those problems of size n over 4 are solved, the way to combine all three of these into the solution to the n size problem, that's going to take n squared time to combine those solutions. But you can imagine now that this n over 4 problem can now be broken down into 3, as can each of these others. How big are each of those subproblems?
And over, what, 16?
Since each one is n over 4, yeah, each one would be n over 16. So you can see how we can start thinking of a tree. How long would it take to take all three of these solutions and recombine them into the solution that is the n over 4 size problem?
Terminology, I always seem to looking at that. I think it's like. Yeah.
Yeah,
There you go.
theta of n over 4
Yeah.
squared.
Yeah, about right.
That's to get from there. back
Yeah,
to-
that's to recombine these three solutions into the n over 4 solved solution. So again, this is a way to visualize this. That recursion just leads to each of these nodes, each of these making 3 nodes as children, each of size n over 4. So let's look at this in terms of a few steps. So step 1 is going to be, we're going to relate T of n in terms of its subcomponents. To recombine this into its solution, it's going to take some constant times n squared time. And each of these 3 children are going to be related as T of n over 4. But each of those needs to be broken down into their children. So how would we figure out the complexity of this entire process? We're going to do this level by level in this tree. What is the complexity of level 0, of level 1, of level 2? And then we're also going to ask the question, how many levels are there? So here's how we're going to do that. This is a bit of a complicated slide. Eventually, these nodes break down into something that is constant. We've reached the base case. So the question is, how many levels are there going to be? If each time we're cutting the size of the problem in 4, in 4, in 4, in 4, then we're going to end up with log base 4 number of levels before we get down to that base case. Does it make sense as to why that is log base 4? You're cutting a problem in half, it's log base 2. You're cutting a problem in tenths, you'd end up with log base 10, going from 1000 to 100 to 10 to 1. That's just logarithmic in base 10. So the number of subproblems that you have is going to be the base of the logarithm for how many steps you need to take to get this down to that base case. But let's start looking at the complexity of each of these levels. You can see that we don't have a complexity associated with breaking the problems down into their subcomponents, but we do have some complexity in putting the solution back together. So once we have the 3 n over 4 size problem solved, to get the n size problem solved, it's going to take Cn squared time, some constant times n squared. Each one of these problems is going to take some constant times n over 4 squared. So if we sum how many problems we have here, we end up with 3 over 16 Cn squared. We can do the same logic at the next level to say we now have 3, 6, 9 copies of C times n over 16 squared. So that gets us to 3 over 16 squared Cn squared. And we can do this analysis and start to see the process emerge for each level. We are adding one term to the exponent, an extra 3/16 to get from here to here. All we have to do is add an extra 3/16 term. The next one would be 3/16 cubed Cn squared. So we can turn this into a sum and figure out what that adds up to. We know that there are log base 4 of n rows to this. So we can incorporate that and say that the total solution to this is going to be in theta of n to the log base 4 of 3. That's this row. Summing all of this up, we end up saying, okay, we're going to sum these terms, but we don't care about coming up with the entire expression. We just need to know the asymptotic order. So when we sum Cn squared with 3/16 Cn squared, that's just a constant. This is also a constant. Whenever we have some number of these, the question is just, do we have enough of them to create a multiplicative extra term to the order? And in this case, we don't. Here we just have, this is the reason why the number of theta of ones lead to that. But as we sum all of these terms, we get to big O of n squared. But it's a nice visual way of seeing the problem broken down. It's just that when you do this, it ends up being quite a bit of work to put together the solution. You're not doing the back substitution on each level, which is simplifying the problem at each step until the pattern breaks. How are we doing? Questions on this? How do we feel at least about the process of breaking the problem down? Kind of building the tree. Can we take the idea of the problem in general? Are we fairly confident in building a tree that represents that recursive procedure? Maybe show of thumbs, how does that part feel for this problem? Okay. How do we feel about the row by row analysis? Show of thumbs again, you have the tree, figuring out the complexity of each level of this tree. How do we feel about that? Getting worse, good to know. And then how do we feel about once we have the terms here, summing them, but from the perspective of an asymptotic order? How do we feel about that? Even worse, excellent. This is what I anticipated. This is where a lot of the practice comes in of seeing that work. So what this is telling me is I probably need to go find a good second example for this, because this is something that it's nice, it's visual, but I thought there might be a little bit missing there. So I'll work on that and come back with another one. Yeah.
When we were talking about substitution before, you were saying that you kind of start out by intuitively kind of figuring out what it should be, and then you that method.
Yeah.
And verify that.
Yeah.
Are we thinking of the recursion tree method as if you can't intuitively figure out what it should be?
Yeah. There's an intuition usually when you know the algorithm. So binary search, when you think about how this operates, you're cutting the problem in half each time. And that tells you there should be a logarithmic number of those levels or those steps. Sometimes you have a recurrence and you don't necessarily know what it ties to, what algorithm it relates. If you don't have that, it's hard to build some intuition on what that is going to look like asymptotically. So I'll come up with another example of this at some point, but these are the three big steps to the recursion tree method. Build the tree, level order analysis, and then sum that level order analysis to get if we're doing the work of each of these levels, then by the time we hit that base case, that is the total amount of work that's been done. Add the work at each recursive level, times the number of levels that we have. It is technically step 4, but step 1 was relating T of n. Write down T of n. I don't really count that as a step. Yeah,
So where does C of n squared come from? Is that because we have big data of n squared and we?
yeah. If it's theta of n squared, we don't know what the constant associated with that is. It could be some small constant, some large constant, but it's the cost of recombining the subproblem solutions into the larger solution. So we consider that to be the cost of this node in that tree is the combined solution order. And it's just how many nodes are there in that level? How many levels are there? What is the cost of each one of them? So we're summing them in the dimension that is on the level order and then summing all the levels to get the combined cost of that. Again, I find this to be a very visual way of breaking down recursion. It can help you to set up the problem. My personal experience is that it ends up being easier to use the substitution method in a lot of cases. But I'll leave that up to you as you mess around with this, as you practice it, both with this and on homework. Let's look at some irregular recurrences. So a lot of what we've looked at so far has a kind of formula with those 3 main pieces: the number of subproblems, size of each problem, recombine cost. But not all recurrences break down into the same size subproblems. It could be that we're going to break a list down into the first 3/4 and the last 1/4 for some reason. So an example to this is, here's a strange recurrence. T of n equals T of n over 3 plus T of 2n over 3 plus theta of n. This means we're breaking the problem of size n down into 2 subproblems, but they are of different sizes. One is 1/3 of the data and one is 2/3. The recombined solution cost here is linear with proportion to n. So this is where the recursion tree can help reasonably well. Let's go ahead and build the recursion tree. Take a second and see if you can take this recursion and draw out what that tree would look like.
Fascinating. Well, it's only get interesting. Alright. Oh. Wait.
We've written down the recurrence. I'm going to go back to that step 4 so that you can look at what the tree from the last problem looked like and what kind of analysis there was there. As you build the tree, start thinking about how deep is the tree, how many levels are there going to be, as well as what is the sum of the complexity of each of the levels of the tree.
Yeah. These things are all at. This is fascinating. It's different, yeah.
Yeah, what have you found?
I don't really found anything, actually, I have a
Question?
question about.
Yeah.
I didn't.
Yeah.
Where does 3/16 come from, first of all? But there.
Yeah, so if we are squaring each of n over four. What is, if we square n over four times n over four, what do we get? Yeah, and then we have 3 copies of it.
Okay, so.
So here's the n squared over 16, n squared over 16, n squared over 16. This is the equivalent of 3 cn squared over 16.
Okay.
Just we're seeing it, but something feels off.
Yeah.
I have a question.
Yeah, yeah. So on Canvas and modules, there is a slides module. I am usually putting the slide deck on Canvas once we finish going over that slide deck. But if you'd like access to it before that gets posted, I can add you to, I can share the slides repository with you, and that way you can go back to what we've seen so far and iterate through that. I just often have problems and solutions on the same slide. Like, as an example, if we go to this point, you build the recursion tree, the very next time I hit the button on this exact same slide, there will be that recursion tree. And if you're looking at the slides in class at the same time, then you see the build the recursion tree, and there's the recursion tree right in front of you. So you don't have that practice of, I find there'd be a lot of value in when you try to do a problem like this, look at what was my best effort without the answer in front of me, then
Yeah.
compare it to the answer, what was missing. And that lets you know a lot of what isn't intuitive to you, what kinds of questions you can ask to move from, because when you are taking an exam, you won't have access to the answer right in front of you, so it's good to know what to study or what you don't naturally think of in those kinds of problems, and that comes from this kind of practice. But that said, not everybody learns the same way. I recognize that, and if there's value to having the slides immediately after class, do note that the lecture recording also does exist. I need to upload the lecture recording before you can go back and look at it. So if you're looking for a lecture recording and it's not up, send me an email. I'll make sure to prioritize it as soon as I have a moment. But yeah, you can either refer back to the lecture video, ask for the slides, and then go back to the slides after class, or there's a lot of flexibility here. I want to make the learning environment that works for you. So I have a default, but that default is flexible depending on your needs. Yeah,
All the slides that are relevant to homework, will they be available to everybody?
yes, absolutely. And if you're looking to review something and it's not up and we've gone over that, I end up getting very busy and some things fall through the cracks. You're looking for something and it's not up, send me an email. I can usually get to that within 5 to 15 minutes if I know, oh, someone's looking for that. It's on a priority list, but it's below the emergencies. But as soon as I know someone's looking for it, it's an emergency. So it comes to the top of my queue of tasks. So you're always welcome to reach out if something you're looking for is not available.
I guess. Same size subproblems. Well, I see what they're talking about a little bit, but something.
Yeah, what does this tree look like? So I'm gonna reveal a solution. As I just talked about, look at what you built and look at this solution and see what the differences are.
Oh, okay. Well, I did have one good idea, but okay, wow.
Yeah, the number of levels here is a bit of a stretch. I'm not necessarily anticipating everybody comes up with the perfect function for the number of levels.
That's actually kind of, that's actually.
But it makes
kind of
sense.
funny, but, yeah, it does make sense, but I'm actually still surprised. Yeah, it's the CN thing that is constant. I actually thought it would have multiplied a little bit, but I suppose I was wrong.
Question?
How do you find the number of rows? Do you have any good methods or tips for us to help us
Yeah.
find the number of rows?
So when we see how many times are we breaking this down into those components, we know, given that there's an imbalance here, that eventually this is going to become T of one, T of some base case size.
Now I get it.
So how many steps do we need breaking a problem into 1/3 and 2/3 in order to reach that size where the size of the problem is one? How many, what is that function based on how n scales? And since we're breaking this down into 1/3 and 2/3, we're basically gonna see that there's an average number of rows here. The right subtree is gonna be deeper than the left subtree. But the average number of rows as we do that is gonna be based on log base 3/2. We get the 3/2 from inverting the deeper part of the tree. You see this 2/3, just like before we flipped that and got the log. We can flip the 2/3 to 3/2, and that becomes the base of your log. And that becomes at least a good estimate, even if you get the log base 3/2 of n. That is proportional to log. That's in the order of log n. So we have Cn, and we're going to multiply that by the logarithmic number of levels. And that's how we get n log n at the end. Each level has complexity n, and there are a number of levels on the deeper part of the tree, the 2/3 part of the tree, that is proportional to log of n.
Okay.
And the reason we're using big O of n log n here
Yeah,
is that base 2 logarithm is going to be more complicated than base 1.5 logarithm. So yes, there is a more specific order that we could relate here, probably. But we know that it is less than or equal to the order n log n. So rather than going into the level of work that we would need to figure out the exact order, we can just give a strict upper bound that says the order that we found is less than or equal to that order.
Now I get it.
How are we doing? Questions on this?
Fractions work again?
In what sense? Where the fractions are showing up,
Just to math, how does math, what's a fraction?
right? If you're feeling relatively lost from this is probably a conversation we should have in office hours. I'm anticipating that some portion of the class is probably somewhat lost putting this together. I would love to have that conversation with you, and a lot of the times conversations in office hours lead to coming back to class and saying, I understand what the general confusion was, let me address that. So you're doing me and the rest of the class a huge favor by coming and talking to me, because I can get a much better sense of what are those confusions so that I can address them in class. So we are out of time for the day. I'll come back and summarize this at the start of tomorrow's class before we dive into the master method. But as always, I'd love to see some number of you in office hours who have recommended help. Yeah.
Can I ask?
Yeah, so the recursion tree here, I figure.
Yeah. Bit hard to see that.
Yeah.
Yeah. At least understanding it better now. Thank you.
Yeah.
I could say. I really did, I am actually kind of surprised, I actually expected a bit more. I did, on the practice, more than I saw, like this. Instead of, you know, it's like outside, but. I think I understand it, but.
Just about everything that's had technically happened on Thursday, right there. I just stated on Thursday because sometimes
Yeah.
this quarter I may need to leave a little bit early,
Like-
have my later class. And that way I would have to cancel the existing office hour. It's basically 12 every day. I'm also around something about 1 to 4 post afternoons. Sometimes I have some things going on or some meetings.
You're right.
Yeah. I'm.
But, yeah. So.
Yeah.
Any other questions on stuff? That stuff.
Yeah, yeah, actually, live streaming this, like you said, and this.
Yeah.
Have it up, we can show that.